Hello, I'm G Platinum and today I'm going to talk about continued fractions. You might have seen them in this form, but this is not what I will be explaining today. What I want to talk about are these kind of continued fractions, more precisely, simple infinite continued fractions, which we can abbreviate like this. Using this notation, we can express square roots using rational convergence, which I'll explain how to compute later in the video. The weird thing about continued fractions of square root is that they are periodic, so their coefficient repeat after a little bit. We can instantly jump in with an example. Let's take the square root of 17. Being between 16 and 25, the integer part will be 4, and then there will be a decimal part that we can write as 1 over x. We can solve for x and get that it's equal to the square root of 17 plus 4, but we know that the square root of 17 is equal to 4 plus 1 over x, and so we get that x is equal to 8 plus 1 over x. So we can go ahead and plug that in the first formula we've gotten and get a periodic simple infinite continued fraction for the square root of 17 that we can abbreviate like this if you prefer. Now I'm going to show you how to get the coefficients for every real number you want. We are going to take it and it will be equal to x0 and its floor is going to be equal to a0. For the next step we are going to take the inverse of the difference between x0 and a0 and it will be the x1, and like the last one, its floor will be a1. Continuing like this, we get the coefficients for the continued fraction. Now we are going to see this process for the square root of 17 and see that it repeats. This part of the video will be about convergence. These are the approximations you get by computing the different extent of the continued fraction. Let's calculate the first 5 convergents for the square root of 17. We see that the fifth already matches for the first 7 decimal digits of the initial number. Now you will see the different steps to calculate the fifth one. This will be a section where I'll talk about particular fractions, such as the fraction for the golden ratio and a non-simple infinite continued fraction to approximate pi. We all know the golden ratio is the positive solution to this second degree equation, and we also know that the golden ratio is 1 more than its inverse. From this, we can pretty easily jump to the continued fraction of this number. We can see that the convergence of this continued fraction are not as accurate as the last, as only in its 10th one we get the first 3 decimal digits right. Here on the right I put a chart of how his convergence isolate up and down. With the pi approximation this will be even more evident. This might seem a bit unrelated, but it's going to help us later. We are going to take a series made up of elements, each one different from the one before and each different from 0. We can consider the difference between the inverses of the first 2 elements, then we are going to take only the denominator from this last expression. I'm going to add and subtract a1 squared and group everything to simplify and get this. From this transformation we can come up with a continued fraction of this kind of series, which you can also write like this, and this continued fraction will look something like this. Obviously we can extend this sum up to infinity and get the same kind of continuous fraction. If you want a rigorous proof, I will link the source from where I found this series in the description. Now we are going to talk of the fraction for pi. We are going to use the series discovered by Leibniz in 1673, which is actually a special case of the Taylor series for the inverse tangent that also has its own infinite non-simple continued fraction that you can find in the same document I talked about earlier. You might have already seen this series somewhere, and using the continued fraction we developed before, we can express it as 1. The terms of this series are all the odd numbers, as alpha k is equal to 2k minus 1, and so on. Now, it's pretty easy to calculate the difference between two consecutive elements, because it will always be 2. So now we have the continued fraction for pi over 4, and if we multiply by 4, we get the expression for pi only. Here you can see the graphs that represent the first 1000 convergents and below the first 5000. I will leave these two images in the description if you want to see them better. As I said earlier, this converges extremely slowly, as you can see from the image.